In sections 3.2 and 3.3, we're going to go back to concepts that we've covered before with functions, namely, is an expression or a relation a function or not, domain and range, and then we're going to talk a little bit more about x and y intercepts and symmetry. What we're going to be focusing on in these two sections that's different than the previous one is the graphs of functions. So let's start with probably one of the most important things, which is the graph that we're looking at a function or not? So if you remember from 3.1, we discussed the difference between a relation and a function. And a relation was any rule at all that assigns inputs to outputs. I'm going to put something in here. Remember, inputs, when we're talking about this class, are the x values and outputs are the y values. Or now we know f of x values. And in a function, it's a specific type of rule where each input or each x value is assigned only one y value or one f of x value. So when we're talking about functions in this section, in this class actually, we're defining y as a function of x. Now, if you go to other types of math classes like trigonometry or calculus, we kind of redefine not y as a function of x, but maybe r as a function of theta or other variables. So you might see different variables used when we're discussing functions, but you have the same definition. It's a rule where every input is assigned only one output. So let's take a look at what that means graphically. Cool. On this graph, I want to draw a curve. I'm going to make it pretty simple. I want to draw the curve x equals y squared. There we go. And here's what I want you to notice about this graph. This graph, if we have an input x, let's say we have the input, I don't know, x equals 1, 2, 3, 4. Notice that if I have the input x equals 4, there are two y values. Sorry, my graph isn't scale. There are two y values that go with it. Now, I happen to know, because I know the equation, that if x equals 4, y could be 2 squared. So I have the ordered pair 4, 2. But also, if x equals 4, y could be negative 2. So we could have the ordered pair for negative 2, which is probably this one down here. So I have one x value, one input that has two different outputs, y equals negative 2 and y equals positive 2. So this is not a graph of a function. Y is not a function of x here. So all this stuff that I just did right there in green, it all depends on knowing the x equals y squared. And I don't want you guys to have to come up with that. So we're going to talk about something called the vertical line test that's a lot easier to do. And here's what the vertical line test says. The vertical line test says if any vertical line, so notice here when we were drawing x equals 4, that was creating a vertical line. So vertical lines go with x values. If any vertical line or any x value crosses your graph more than once, that means it has more than one y value, more than one output. Then, let me scooch our graph up just a little bit. Then that graph is not a function. So if any vertical line crosses your graph more than one time, then that graph is not a function. So here is our vertical line that I can't draw very well. There's our vertical line. It crosses 2 times here in here, so we know that it's not a function. And just really quickly, that's because vertical lines are x values. They represent x values. And when they cross your graph, those represent y values that are associated with them. Okay, so let's use this vertical line test now and some other concepts to talk about domain and range as we analyze some more interesting graphs. Cool. Here are 3 excellent examples of graphs. Man, not one of these graphs is a function. So I'm going to call this examples 1, 2, and 3. And for your notes, you do not need to copy down my angry man graph here that you may recognize. I love this. This is from trigonometry. This is a rose, a 6-petaled rose, and this is a limacon, a cardioid. These are both from trigonometry, and this is just Desmos. This is just fun with Desmos. So the first thing we're going to answer for each one of these is this a function or not? And to answer that question, we're going to look at the vertical line test. So the question will be, can you draw any vertical line at all that crosses your graph more than once? So in other words, does any vertical line cross your graph twice or more? If the answer is yes, then the question is, the answer to the question is that it is not a function. Okay, so if you notice for each one of these graphs, they all fail the vertical line test. None of them are functions. This very angry gentleman here, I can draw a semi-vertical line that crosses the graph there and there and there and there. So that would definitely be not a function. This lovely rose in the middle here, I could draw a line way over here. A lot of students say, well, Mary Beth, I can draw the vertical line way out here and it doesn't cross at all. But you just have to find one vertical line. So, okay, here we go. There's a vertical line that crosses the graph twice. So this would also be not a function. And this lovely limacon on the far right is also not a function. Here's a vertical line there that hits 1, 2, 3, 4 times. So this would also be no, it's not a function. I promise to have some examples that are functions, but I wanted to show you real quickly with these 3. So let's extend, and let me clean this up a little bit, and let's extend this to talking about the domain and range of these graphs. There we go. Okay, so as a reminder, the answer to each part A is these are not functions. Because each one of them failed the vertical line test, we could find a vertical line that touched our graph more than once. It didn't matter that other vertical lines didn't touch the graph, just could we find at least one. So none of these graphs are functions. So let's move on to talk about something that's a little bit more exciting. Let's talk about domain for each of these in part B. So now if you remember, domain was all of your x values. Now each one of these graphs has an infinite number of x values here. This x values start way back here at, what do you think that is? Negative 300 is here. Negative 350 is here. So maybe they start here at negative 375. And it looks like the x values, there's a bunch in the middle here. There's all these x values in the middle that are in our graph. but the x values don't exist way over here. Our graph isn't way over here on the right, so the x values end about, looks like that's the farthest point to the right. I'm going to say that is 298. I'm going to kind of make that up. Okay, so our x values for this angry gentleman here go from negative 395 is the smallest x, and they go up to 298, that's the largest x, and they don't have any open circles at negative 395 or at 298. So they include those x values, so I'm going to put brackets at each of those. So my domain is all the x's, an infinite number of x's, and they're between negative 395 up to 298. Now in a second we're going to talk about the range, but before we talk about the range, I want to do the domain for the middle one. So this domain, for the sake of simplicity, let's say this is negative 6.2. And let's say this over here is positive 6.2. So for our domain, which I'm going to shorten to D, remember these are the x values we're looking at. There's an infinite number because there's all these x values in between those two. But for the domain of this rows, it looks like we're starting at negative 6.2 and we're ending at positive 6.2. And for the rows on the far right, definitely starting at negative 6 for our domain. And the x values end at, let's see, that's probably like 0.3. Now, I absolutely am eyeballing, and if you're being evaluated on a quiz or a test or my math lab, you will be given exact numbers like this negative 6 here. Okay, next thing, let's talk about the range. So I'm going to do range in red. Now, you probably remember that the range is the y values. Since there's an infinite number, I'm going to write these in interval notation again. So let's see, for our first graph here of this angry face, the smallest this graph goes on the y direction is 0. It starts at his chin at y equals 0. So the smallest y is 0, and the biggest y is, you can't see that, but that's at 800. It goes up to 800. The range for the rows here, let's see, the smallest it gets is negative 4, the lowest it gets, and the highest it gets 5, 6, 7. So the range for the rows is the smallest the graph gets is negative 4, and the highest the graph gets is 7. And these are just the y values. So this is the smallest y, or the bottommost y, and the topmost y. And then finally for our rows, for our limacon here, these are so cool. Looks like it starts down here at, let's say, negative 3.5 and goes up to positive 3.5. So our range would be negative 3.5 to positive 3.5. Cool. Okay, before we move on to the next topic, I want to discuss symmetry, because there's a lot of graphs that have symmetry, especially in artwork and definitely in mathematics. But we want to discuss the difference between this graph that is not really symmetric at all. There's no place that you could put a mirror and have an exact reflection on both sides. But this really elegant rose in the middle definitely has symmetry all over the place, and so does the limacon at the very, very right, has symmetry, lots of symmetry to it. So there are 3 different types of symmetry that we're going to discuss in this class. And they are symmetry about the x-axis. In other words, if you put a mirror on the x-axis, do you have a reflection, a perfect reflection on the top and bottom of the x-axis? Symmetry about the y-axis. So same thing, if you put a mirror on the y-axis, do you have a reflection, a perfect reflection on the right and the left of the y-axis? Symmetry about the origin. That's symmetry if you put a mirror along a diagonal that goes through 0, 0, do you have a mirror reflection on diagonally through the origin? Or none of these? Now, there are tons of other types of symmetry, so we're not asking, is there any symmetry at all? Just does it have x-axis, y-axis, or origin? Or none of these. Now, obviously, the angry man has none of these types of symmetry. There's no symmetry at all in this graph. There are slight symmetric things like his eyeballs are symmetric and his ears, but not about the x-axis or the y-axis. The rose, on the other hand, does have symmetry. So let's see. If we put a mirror on top of the x-axis, do we have a reflection on the top and the bottom about the x-axis? No, there's only one petal on the top and there's 2 on the bottom. But if we put a mirror along the y-axis, there is symmetry to the right and left, or about the y-axis. So we do have y-axis symmetry here. And if we put a mirror along the origin, through the origin on a diagonal, do we have symmetry, the top and the bottom of that mirror? And the answer to that is no. There's not a reflective symmetry to the top and the bottom of the diagonal line. Okay, let's go to the last one, to the limaçon. This one does have x-axis symmetry. It's symmetric about the x-axis, or to the top and bottom of the x-axis, but not y-axis or the origin. Okay, let's look at 3 more graphs. So let's ask ourselves the same 4 questions for these 3 examples. Is what we're looking at a function, meaning is y a function of x in the picture? What's the domain? What's the range of that function or of that relation? And is there symmetry about the x-axis, y-axis, origin, or none of those? Okay, let's look at the first example on the left. So is this a function? Is there a way that we can draw any line, vertical line, through our graph that would hit twice or more? Well, sure. Could draw a vertical line right here that hits about 100 times, right? It hits there and there and there and there and there and there and there. Heck no, that is not a function. What's the domain and what's the range? I apologize because I just shamelessly stole these graphs from the internet. But for simplicity's sake, let's say for the domain, it starts way over here at -3.5. So it starts -3.5 and it goes up to here on the far right. That would be at, like, let's say 3.1. Apologies for guesstimating. The range of that function, how high and how low does that get? Okay, so my eyes are old. I would say probably 3.1 is at the top, and at the bottom, -3.1. So -3.1 to +3.1. Let's see, symmetry. Well, if I were to place a mirror on the, x-axis is first. On the x-axis, I don't have a perfect reflection top and bottom. It's kind of tilted. So no x-axis symmetry, and same issue with the y-axis. There's no mirror reflection to the left and right of the y-axis. It's skew a little bit. However, if I put a mirror on a diagonal line going through the origin, there is symmetry on the top and bottom of that line. So this is a great graph of something that has symmetry around the origin. Okay, middle function. Ooh, did I use that word appropriately? Is there a vertical line that hits this graph 2 times or more? Man, I don't think so. All of the vertical graphs I'm looking at, this is kind of like a bouncing ball graph. All of the lines I'm looking at only hit 1 time. So this is a function. In other words, every vertical line, every x, only hits our graph 1 time. Okay, I'm going to erase those vertical lines because I need to see well to answer my domain and range questions. So for the domain, now this graph does not extend into the negative x region. It doesn't extend to the left of 0. It also doesn't have an open circle. So this graph's domain must start at x equals 0 with a bracket, but it doesn't stop. It's the bouncing ball and it goes on forever. So don't put the end of the window you see, put the edge of the graph if it does stop. This graph doesn't stop, it goes on forever. So the x's start at 0 and go all the way to the right, and we never put a bracket on an infinity, so this domain would be 0 to infinity, bracket on the 0, and a parenthesis on the infinity. And then finally, the range. The lowest this graph gets is 0, and it bounces off of 0. There are no open circles. And the highest this graph gets, one of the reasons I chose it, because my old eyes can see this, is 1. Whoops. And it does equal 1. There is no symmetry whatsoever about this graph. Definitely not symmetric about the x-axis or the y-axis or the origin. So this would be a great example of something that has no symmetry. Okay, and then our last cool example, this starburst thing here. Let's see. For the sake of simplicity, well, let's do the function first. Definitely not a function, right? A bunch of vertical lines hit this graph more than 1 time. So this would be a no. The domain, so how far to the left and right. So for the sake of simplicity, I'm going to say this is 22 and this is negative 22. So negative 22 to positive 22. There are an infinite number of x's in there because there's negative 21 and negative 20 and negative 19, and then there's all the decimals and the numbers in the middle there. So there's an infinite number of x's in here, represented in here. I think the range happens to be the same. The lowest the graph goes also appears to be negative 22. And the top of the graph is up here. That appears to be the same, positive 22. Cool. This one is super cool. Let's see. It looks so symmetric. So let's check x-axis. If we put, it's not symmetric about the x-axis. If I put a mirror right here on the x-axis, it's not a perfect reflection above and below the x-axis. What about y-axis? Ooh, now that does look like it's symmetric. If I put a mirror on top of the y-axis, it is a perfect reflection to the right and left. So it definitely has y-axis symmetry. And then as far as the origin goes, if we drew a line through the origin, let's see, it almost looks like it has symmetry through the origin, but because this petal, for lack of a better word, think of it like a flower, this petal here is just a little bit above the x-axis. Symmetry through the origin would mean that its counterpart would be off a little bit to the side of the y-axis. So that does not have symmetry through the origin. Okay, so these are just pretty picture graphs. Can we do some that are more like what's in your homework? Let's look at these. So for these, I just want to focus on writing the domain and the range. I think the vertical line test is pretty easy. And only one of these graphs has any kind of symmetry, and that's this bottom middle one. It's symmetric about the y-axis. So I just want to focus on domain and range for the sake of time. So our first example here in the upper left, the domain starts at -1 for the x's, goes to 3. And since I very emphatically put closed dots, although I didn't have to, then there's brackets, -1 to 3. For the range, the lowest the value gets for the y's is 2, and the highest it gets is 6. So I'd put bracket 2 to 6, another closed bracket. Okay, that one's usually not so bad. Just remember, keep in mind, you're not writing ordered pairs, you're writing intervals. Smallest x value, largest x value for the domain, smallest y value, largest y value for the range. Okay, let's do the middle one. Let's see, the smallest x value for the domain is -3, but it has that, if you can't see, that's -3. It has an open circle there, so I'm going to put a parenthesis at -3. I can't put -2.9 because then I'd be closing out -2.999. So wherever I stop my 2.999s, I'm missing a bunch. So I have -3 as a boundary. It can go right up to -3. It just can't equal -3. And then the farthest to the right, oh, it goes forever to the right. So up to infinity. For the range, the smallest in the y value that our function gets is -4. And it equals -4 for a while. There's a big horizontal line at -4. Now this one always throws people. I get a lot of people that say, and then the highest this graph goes is -2. But that's not true. The graph goes way above -2. If you look at the graph going up to the right-hand side, the graph actually goes to -1 and 0 and 1, and then there's an arrow. So this graph goes up forever in the y direction. So the range would be bracket -4 up to infinity. Okay, let's look at the one on the far right. And actually, let me pull this, if I can, over a little bit. There we go, much better. Okay, so domain for part A. Let's see. Oh, the farthest to the left, it goes on forever to the left. The x's go on forever to the left. So this would be -infinity to the left. But it does stop on the right-hand side. It's stopped. The biggest the x's get is 4. There's a big fat dot right there at 4. So it stops at 4 with a bracket. For the range, the lowest the y values get is here. So that's at -2. Y equals -2. And the highest the y values get is +4. That tops out here at 4. Okay, so the range is -2 to 4 with brackets. Let's see, let's do the fourth one down here. The domain starts at -1 with an open circle, so parentheses, but then goes all the way to the right because of the arrow. So -1 to infinity with parentheses. And the range, well, the lowest that the graph gets because of the arrow is -infinity, but it stops at the top up there at y equals 4. And since there's an open circle, I'm going to put 4 with a parenthesis. Okay, the one in the middle, for closed captioning reasons, I'm going to, just in case, I'm going to put the domain at the up here and the range up above the graph. So let's see, the domain, the farthest to the left the graph goes is -infinity. but it stops in the middle here. It has a break. It doesn't have any values between -1 and 2. So this domain would be -infinity to -1. That would get us to here. And then it takes a break, union, picks up again at 2, and goes to infinity. The range, on the other hand, starts at y=0 and goes all the way up to infinity. The x values have a skip in them. There are no x values for our graph between -1 and +2, but the y values don't have that skip. They have y=0, y=1, y=2, all the way up to infinity. Okay, last one, and then we'll move on to our last topic. The domain and range here. So I think I'll do the same thing. I'm going to go up here and do domain. So domain, man, this graph has no breaks in the middle, all the way to the left, all the way to the right. So this domain would be -infinity to +infinity. The range does go all the way to the bottom, so -infinity, but it stops out at -2, actually twice, so -2 with a bracket. I wanted to do an example that's really similar to a lot of problems found in your homework, where we give you a function, in this case f of x equals 3x squared minus x minus 2, and then ask a bunch of follow-up questions not giving you the graph. So I want to show you how to do these problems. So part A says, is the point 2, 8 on the graph of f? What I do not want you to do in this case is try to graph it using Desmos or a graphing calculator. Instead, remember that the ordered pair is an x and a y. So if you're checking if 2, 8 is on the graph, that would mean the same thing as asking x equals 2 gives y equals 8. So let's plug in x equals 2. So we'll do f of 2 is 3 times 2 squared minus 2, and do some arithmetic here. So this is 3 times 4 minus 2, which is 12 minus 4, which is 8. Cool. So since we plugged in x equals 2 and got out y equals 8, the answer to that question is yes. 2, 8 is on the graph. Okay, let's do part B. So part B says, if x equals -1, what is f of x? And the follow-up, what is the point on the graph of f? So if x equals -1, let's figure that out. F of x would be f of -1, 3 times -1 squared minus -1 minus 2 gives us 3 times 1 plus 1 minus 2, which is 3 minus 1. So f of -1 is 2. So to answer the first question, what is f of x at x equals -1? F of x is 2 at x equals -1. And the point that is on the graph is the ordered pair x is -1 gives us f of x, or y, is 2. Okay, let's talk about C after I clean this up a little bit. There we go. C says, if f of x is -2, what is x? Ooh, that's different than B. B gave us the x value and had us find the f of x value. C, f of x is equal to -2. So that would be -2 equals 3x squared minus x minus 2. And now we have to find x. Okay, so Oh, we've got a squared. Let's do some algebra. Let's get 0 on one side. Maybe we can factor. So adding that 2 to both sides gives us 3x squared minus x. And I can factor out an x greatest common factor, 3x minus 1. So I have x equals 0, 3x minus 1 is 0, giving us x equals 0 and x equals 1/3. So the points that are on the graph, to answer their follow-up question, would be 0 goes with -2 and 1/3 goes with -2. Those would be our points on the graph. Okay, let's talk about domain. So the domain for part D, remember, when you're looking for domain like we did in the last section, you're just looking for two things right now. Are you ever dividing by 0? Are there any x values that would make us divide by 0? And are there any square roots that might have negatives inside the radicand? We don't have any square roots and we don't have any place where we divide by 0. So the domain for this function would be all real numbers. X can be anything. -infinity to +infinity. There's no restriction on x whatsoever. I think I can put the x-intercepts on here and the y-intercept definitely. And so let's see. Let's do x-intercepts. Now remember, when you're finding an x-intercept, that's setting y equal to 0. So this would be, and y is the same thing as f of x. So this would be 0 equals 3x squared minus x minus 2. Let's see, how do we solve that? I hope that factors. Yep, sure enough, this factors to 3x plus 2 and x minus 1. So we have 3x plus 2 equals 0, which would be x equals -2/3. And x minus 1 is 0, so x equals 1. So we can list these as our x-intercepts. If we had to put them in ordered pair form, it'd be -2/3, 0, and 1, 0. Just depends on how they want us to write them. Now, I normally wouldn't smush quite so much, but I think we can fit f right up here. It says list the y-intercept, if there is one, of the graph of f. Now remember, for the y-intercept, that's my favorite one to find, that's where we set x equal to 0. So f of 0 would be 3 times 0 squared minus 0 minus 2, but that's just going to be -2. So depending on how they want you to write it, if they just want the value for the y-intercept, type in -2. If they want it as an ordered pair, 0, -2. Cool. There's one last concept that we need to cover in section 3.2 and 3.3, and that's the idea of even functions and odd functions. So even functions have a lot of symmetry. They actually are symmetric about the y-axis, and odd functions are symmetric about the origin. And here's how you're going to tell that a function is even or odd. An even function has the property that when you plug in -x instead of x, everything simplifies and the negative disappears. So, or simplifies away is a better way of saying it. So f of -x simplifies to just be f of x. So an example of an even function might be this. F of x equals, let's say, 5x to the 4th minus 8x squared. It gets the term even, by the way, from the even exponents. But watch what happens when we do this substitution. To check to see if it's even, we're going to replace we're going to replace x with negative x and see what happens. So everywhere I see an x, I'm going to put parentheses just like we were doing in our previous section. And then I'm going to put negative x, I forgot the squared, in for those spots. So it will be 5 parentheses negative x to the 4th minus 8 parentheses negative x squared. And what's cool is because these negative x's have even exponents on them, they simplify. Negative x to the 4th is just x to the 4th. So f of negative x is 5x to the 4th. And likewise, negative x quantity squared is x squared minus 8x squared. But this is the same f of x that we started with. So that function is even. That also means that it's symmetric about the y-axis without even having to graph it. Now, odd functions are great because odd functions, you check them exactly the same way. You plug in negative x instead of x. And what simplifies is the negative can be factored out in front of the function. So for example, say you had the function f of x equals 10x to the 7th minus 8x to the 5th. Okay, so to check that, we're going to do exactly the same way we checked for the even function. We're going to plug negative x in for x and see what happens. So let's see, everywhere I see an x, I'm going to replace it with parentheses. So 10x to the 7th is 10 parentheses to the 7th. And 8x to the 5th is 8 parentheses to the 5th, and I'm going to put that negative x in there. Okay, and then simplifying this, let's see, a negative x to an odd exponent, hence the term odd function. Negative x to the 7th power is negative x to the 7th. So this is 10 times negative x to the 7th without the parentheses, with the negative on the outside. This is negative x to the 5th is negative x to the 5th. So we have negative 10x to the 7th plus 8x to the 5th. And if we factor a negative out of that function, we have negative times the quantity 10x to the 7th minus 8x to the 5th, which is the same thing as the negative times the f of x. So this would be an odd function. Let me show you one more quick one that's neither. So for our very last example, let's check to see if f of x equals, this should look familiar, 3x squared minus x minus 2 is even, odd, or neither. So notice the way you check for even and odd is the same. So what we're going to do is plug in negative x instead of x. Everywhere I see an x, I'm going to put parentheses. So 3 parentheses squared minus parentheses minus 2. And then I'm going to put that negative x into those parentheses. So the first set of parentheses, because of the squared, negative x quantity squared is just x squared. So we have 3x squared. However, the second set of parentheses doesn't have an exponent, so it must be a 1. So negative x is positive x, and then minus 2. Clean that up just a little bit. That's better. Okay, well, this is certainly not the same as f of x. So this is not 3x squared minus x minus 2. So it's not even. If we were to factor out a negative, we would have negative 3x squared minus x plus 2, which is not negative 3x squared minus x minus 2, so it's also not odd. So this would be neither. One way you can tell it probably is neither even nor odd is it has a combination of even and odd exponents. That's just a rule of thumb. Don't use it all the time, but it's a good indication it's probably neither.